And we have different types of simulations. So Jim just talked about classical MD, so I won't cover that. In quantum chemistry, we focus on two significant tiers of methods. First is density functional theory, which has lots of different flavors. Background before, so it's sort of MD oriented. And ab initio molecular dynamics is sort of the most. It's a very common way of doing one type of simulation, and then there's a whole other group of people who don't do dynamics. They compute properties in a sort of spectral way, and that's more the sort of traditional chemistry style. And then there's quantum chemistry with wave functions, so actually, solving Schrodinger equation in some formalism. And that has lots and lots of different flavors. People joke about there being a Baskin and Robbins, 31 flavors of DFT. I know in NWChem we have at least twice that many flavors of DFT, and there's whole. I've seen papers where they define at least 100 acronyms. You need at that point an appendix. So there's lots and lots of different methods. So I'll try to cover the basics. So this is actually NAMD. This is ALCF user Benoit Roux, just to show the scope of things. So they do lots and lots of atoms for what is, in my opinion, as a quantum chemist, a lifetime. Nanoseconds is eons for a quantum chemist. I won't belabor that. So if you as soon as you turn on the quantum mechanics, you basically lose 3 orders of magnitude in both directions. So you now go, that's a typo, this should be picoseconds. I have 2 different versions of these slides. I'm not using version control like I should. So you go down from give or take 1 million atoms is being feasible. Now you do 1,000 atoms, and you now go from nanoseconds down to picoseconds. So you've really ramped up the computational cost, but presumably the accuracy too. Quantum chemists also focus on wave function theory, where we have things like perturbation theory and coupled cluster theory. Quantum Monte Carlo is sort of it's sort of like the cousin you only see once a year. It's funny. There's a bunch of really OCD people who, even though their methods are only good to 10 to the minus 4, really obsess over getting 13 digits of reproducibility, and you tell them that somebody's solving something with a stochastic integrator using random numbers, and they get really, really scared. And yet Quantum Monte Carlo is an extremely general purpose and reliable method. But I won't talk about it. It's not my thing. We've got some very talented people at ALCF who do that, so I don't have to worry about it. But now we drop at least another order of magnitude, if not 2, depending on which audience I have. The time domain of quantum chemistry, I've used LOL there instead, because you're time stepping at sort of you think about the energy scales and the length scales and the time scales, and how you could time step at like attosecond. You could take an attosecond time step, every so many wall minutes, and then maybe you could do, if you're lucky, a few femtoseconds of MD if you used a really expensive method. This is a standard model. I don't know that quantum chemists, I don't know where you read this. I guess it's in a few places, but you start with H psi equals E psi. So you first say that this molecule lives in its own private universe. So when we do quantum chemistry, we don't include the fact that quantum mechanics tells us that you have to know about every other electron in the universe. And then you throw out relativity, general and special relativity. You throw out the fact that you can create and destroy virtual particles and vacuum effects, all stuff in quantum electrodynamics. You usually or almost certainly throw out another form of relativistic effect called spin orbit. And then you separate electron and nuclear degrees of freedom, and that's sort of what's called the cows and flies approximation. That a cow weighs a whole lot more than a fly, and so the flies really see the cow as a stationary object, even though the cow sees itself as moving along, through the pasture. So the electrons are the flies and the nuclei are the cow. So basically you just assume that the cow doesn't move, and you could model the flies relative to a fixed cow, and that's a good approximation. You could do the relative masses are a factor of 1700, and so you can do sort of the energy coupling. So this gets you to non-relativistic electronic Schrodinger equation in a vacuum at 0 temperature. So you've already thrown out huge swaths of physics. Many, many Nobel Prizes in the 20th century are now completely eliminated from the physical picture of the problem we're solving. We've gone back to somewhere in the mid-1930s in terms of our understanding of nature. And we're nowhere near able to solve the problem. We have this nasty partial differential equation that has singular Coulomb interactions and has this nasty anti-symmetry property that Wolfgang Pauli taught us about, and really doesn't enable us to use any of the sort of traditional PDE solvers that one might expect. What we can do is we can reformulate the problem so that anti-symmetry of the wave function is sort of built in by construction. That comes in something called second quantization, which is sort of an algebraic formulation of anti-symmetry and determinants. And then you take all those operators that came out of all your physics and you project them into some basis set. Chemists use Gaussian orbitals, localized functions. Physicists use plane waves. That has to do with whether or not periodic boundary conditions are relevant. There's other basis sets. People use numerical basis, finite element basis. At the end, I'll talk about pseudospectral. Whenever I talk to finite element people about the way we do basis set projection, they always look at me like I'm a voodoo witch doctor, because the way we do that is not satisfactory to people who do applied mathematics for a living, for the most part. So please don't look behind the curtain. It works. It doesn't have to be derived. That's my hand wavy. Anyway, so then how do we solve this thing? So then we say, okay, well, n-body problem is ridiculously hard in quantum mechanics, so let's just do a mean field solution. Let's take all n-1 particles that I see and just view them as an average quantity, as a background field, and then iterate on that self-consistently, and then recognizing that we are wrong, then try to get back out from that terrible approximation, which is actually really, really accurate in an absolute sense, with many-body perturbation theory or something like that. Or, well, we expand in a sort of series. Now, if we don't truncate that series, that has something called full configuration interaction. That problem is still impossible. So we've now basis set projected and now done a wave function expansion, and we're still, again, nowhere near solving the problem. Full CI methods can be used for systems with 2 atoms. You can get up to maybe a few dozen electrons. Actually, no, I don't even think you get to 2 dozen electrons. It's basically the most gigantic eigenproblem you can possibly imagine. So we can truncate that expansion and truncate it in a variety of different ways, and solve those equations, truncated equations iteratively, and then we can add more corrections via perturbation theory. And this would get you to something called CCSD parenthesis T if you went down this path a long way. So you've made like 15 approximations or something, and you get to a very expensive and accurate method. That's just sort of the flow chart for how we get to where we're going. One of the things that we can do, of course, I said we threw out 75 years worth of physics. We can recover some of those things back in as a posteriori error corrections with perturbation theory. So you can say, now that you've solved this problem, the reason you threw relativity out from the start was because you knew that it was small. Well, knowing now that it's small, you could recover it with perturbation theory, because that's what perturbation theory lets you do. So you use your non-relativistic solution as a 0th order and expand on 1st order or some perturbation theory. And you can add non-adiabatic corrections to assume that the cow starts moving again, and you could do solvent corrections, so you can start including some environment. The atom no longer lives, or molecule no longer lives in a private universe. And then you could even open the system up to basically energy flow, and that's pretty rare, but there are people working on open quantum systems. There's a lot of very interesting problems now that sort of correspond to an open quantum system. So that's our physical world. Now I'm going to switch gears and talk about software, but I just felt like it was worth defining the problem space. NWChem has been around. I think it was initiated by Tom Dunning. So Tom Dunning was at Argonne and sort of had a vision for what the future would look like in computing, and had a unique opportunity to go out to PNNL and get a very large amount of block funding, which allowed him to basically start a big new project, which was NWChem as part of the EMSL construction project. And there was a bunch of people back when they were our age. These people are now, well, at least the 3 that are living are very now senior people. Jeff Nichols is the associate lab director at Oak Ridge. Ricky Kendall was head of the scientific computing group at Oak Ridge, and Robert Harrison is head of an institute at Stony Brook. Back when they were our age, they were working on NWChem, so that's how they cut their teeth. And Jarek Neploka, who died of cancer a couple years ago, was hired. PNNL stole him away from Argonne with a staff offer, and he was the guy who led the Global Arrays project from its inception. The software architecture of NWChem has always been well thought out, at least in theory. There's a distinct emphasis on getting sort of the Cartesian product of the features you have. So if you make a statement that people want to compute energies, gradients for geometry optimizations, frequency calculations for structural analysis, dipole moments for infrared intensities, if you make that statement that those are things that people want, and then you also make the statement that you want to support density functional theory, perturbation theory, and coupled cluster theory, you want to ensure that all 5 of these things work with all 3 of these things. And it's not just that the person who does DFT then supports these features in a specific way, and then that wheel has to be reinvented. You don't want this wheel reinvention happening in all these for-all loops. So you really want to find a way to factorize these things and be able to sort of get all of the end features that are compositional for every method and things like that. So that's really what this is about. This is about the fundamental quantities that the chemists are interested in, the different types of methods that people are interested in, and then all of those things, how they are composed. So you want to represent a molecular geometry regardless of what method you're doing. You want to represent your basis set regardless of what method you're doing. And you want to have dense linear algebra methods regardless of what method you're doing. So you want to factorize these things. So one way to think about this is cake. Cake is tasty, but cake, you have a sliced cake, and then you have some frosting, and then you have some cake, and the frosting is sort of the glue between these. But you don't know until you cut the cake in half if it's vanilla, chocolate, vanilla, or maybe it's chocolate, 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 or chocolate, strawberry, chocolate. You should be able to switch out the cake, and these layers allow you to compose things together. So this is really sort of the top part of the cake, and then the middle part of the cake, and this is this computer science part of the cake, which you would really, really like to coat with an extremely thick layer of frosting and not allow any chemist to really get a hold of, because when they do, bad things happen. And then sort of the cross-cutting element of NWChem that is, I think, underappreciated is something called the runtime database. So this is basically, nowadays there's a whole bunch of open source tools for things like this, but the RTDB is essentially a great way to get fault tolerance, because you basically write a whole bunch. As you do something, you write it out into the database so that if the job fails, you can restart from the database. The other thing is it's a quick and dirty hack to work around the fact that Fortran doesn't give you object orientation. So if you want to embed a whole bunch of parameters and then be able to pull them out, it's sort of like a wormhole to tunnel between different subroutines. So you can say dump a whole bunch of state into the RTDB and then go into another subroutine and go get that back out. And it prevents you from having to pass something that other libraries will do, like hideous arrays of basically gigantic integer arrays that try to represent some sort of object, or having to pass numerous arguments, 57 arguments to a Fortran subroutine is just a terrible idea. So these are sort of, you could think of this as a practical solution to the Fortran problem of the time, or as a really elegant way to capture composability in simulation and resilience. And the key element of this is you're really trying to firewall things away from people who don't have any business touching them. They're very, very talented chemists who are very bad programmers, and there's very good programmers who don't know anything about certain quantum chemistry methods, and that's perfectly reasonable. You want to factorize your code so that you can have people working on their best efforts and not getting bogged down in things they don't understand or care about. These are not exclusive epochs. This I just sort of tried to make something up that would be representative. It'd be nice if I had a Gantt diagram for this, but I wasn't around obviously for most of these phases. But the beginning phase I talked about last week, Oosterhout scaling. The Oosterhout phase is you want to just get stuff working. So I know they spent a lot of time trying to just figure out what best practices were. This is the beauty of block funding. You could take some risks and try and prototype things. They prototyped global arrays. They tried to figure out how global arrays would be used, what was the right design of global arrays. They had a few things that didn't work. They refined them and they got better. And they tried to really develop a coding style and a whole lot of other things that sort of were going to get baked in and had to be done right. Sort of the next phase, and I've looked at very old versions. The oldest version I could pull out of converted CVS into SVN repo was, I think, somewhere around version 3.0. And back then it was really it was a meat and potatoes code. There's basically a handful of methods that quantum chemistry relies upon. Hartree-Fock, MP2, and CCSD, parenthesis T, are really key. So they weren't trying to go after, newfangled methods hot off the journal printing press. They were trying to really go after the meat and potatoes of the field and do them right, and then scale them out, and they were successful. And then they started to grow the method collection. So you see that they introduced density functional theory and a bunch of other methods, and then sort of there's a whole lot of first parallel of its kind. So I don't know, how many of you have seen the movie Half Baked? Probably you have to be a little bit older, I think, to have remembered it when it was out. But there's a line in there where the guy's talking about, like, yeah man, have you ever had ice cream? Well, have you ever had ice cream on weed? Anyways, I apologize to our funding agencies for the drug reference, but so it's sort of like, I like to make the analogy, have you done X? Well, have you done X in parallel? There's a whole lot of, seriously, if you could do X in parallel, you could do a whole lot more of X, you get a whole lot more science. So at the time, you had a lot of codes which were still stuck in the sort of vector age, and we didn't have vector processors like we do now with GPUs and such, so you would just time out. If you couldn't do the problem in 14 days, you couldn't do that science. Or if you couldn't fit it into your hard drive, you couldn't do that science. Well, now you get MPPs, you get distributed memory, you get distributed file systems, and NWChem enables things that are just fundamentally new scientifically just by having a parallel version of core methods. There's a lot of overlap, especially in 4 and 5. One of the things that really happened, I think, just before I got there in the 2000s, was that NWChem really became a robust community code with, they had, I think the last time I checked, 6,000 users. And what I think is interesting, there's probably a period where people would use their favorite code until they ran out of computing power, and then they'd switch to NWChem. And then at some point, I think certainly when I started using it, people were using NWChem as their code. Like, they would use NWChem on their laptop, they would use it on their cluster, and they'd use it on a supercomputer because it was sufficient to cover the space of problems and wasn't just sort of a, oh, now I have to use NWChem type fallback. And when people start sort of using a code designed for supercomputers on their laptop, I think that's sort of a key moment in its existence, can really grab hold of a broader community. Then the thing that I was fortunate to be a part of is really developing some new breakthrough capability. There was someone who came before me, developed a tensor contraction engine as part of a very large project with CS people and chemists to automate many-body theory. And then I worked with Carol Kowalski and added a whole bunch of new functionality that was very much a half-baked of doing a bunch of things in parallel for the first time and doing problems that were previously impossible. And people started adopting NWChem as a platform to do research. So there were academics who were developing totally new methods, and actually they were first implemented in NWChem. And that's cool when people want to use your code as a research platform and not just a black box. And then so now I think we're very much still in 4, 5, and 6, 6 being to petascale and beyond. So NWChem today is running, some parts of NWChem run very well on petascale machines, and other parts do not scale to all of a petascale machine. And then of course we know that petascale is just at the doorstep of much, much larger machines to come with novel architectural features that we'll have to adapt to. So some of the challenges, some of this is a repeat. It's hard to find parallel programmers who also have domain expertise. This is, I think, a challenge for everyone. But I think there seems to be some cultural differences in chemistry. I think in certain engineering disciplines, at least maybe I just encounter a very special subset of engineers, but there seems to be some emphasis on we're engineers, we program, or we're CFD people, we write MPI code. I would say the majority of computational chemists today don't fully appreciate version control. I mean, maybe it's changing now with graduate students, but at least when I was in grad school, things that are just absolute de facto, how can you live without them, things in other fields of computational science were not practiced. And that, of course, evolved that backwards in time to the mid-90s, and there was certainly not a lot of people available. There's a challenge, as I mentioned last week, of trying to do object orientation in Fortran 77, the pre-MPI era and the portability challenge of having your own communication library. Then there was some things where people would, compilers wouldn't do their job and people would decide to create abstraction for performance. So you find out, oh, compiler won't implement inline small functions. So I'll just replace the function call that's supposed to be accessing private member data that I've tried to hide away for good reason so that someday I could change that object. And instead, now we're doing direct access on common blocks. So the common blocks shouldn't have been there, but they had to. But at least if you have a function call API around a common block, you can change everything around internally. But the moment that somebody wants to do direct common block access from a different part of the code, you now hardwire that design forever, unless you fully understand all the dependencies, and they're certainly not obvious. And I think that like any code that was designed in the 90s, it's amazing the world in which we live in terms of free and open source with version control and all these wonderful tools that are out there, all the resources. Look up what the state of the art in open source software practice was in the 90s. CVS was amazing. Good old-fashioned classic Make was amazing. I don't know what there wasn't a whole lot of other power tools that we're used to. And one of the other challenges, of course, is I think Paul alluded to is sometimes funding sources realize they get very satisfied with what they see. You've been extremely successful, and they assume, oh, well, this is good. We don't have to fund this anymore because it's good enough, right? So the code will just, of course, coast. There was no, and I think this is a real challenge for NWChem. NWChem is bigger than it's ever been before, and it's a more pressing need than it's ever been before because all of our machines are parallel, and NWChem is one of the only codes that is all parallel. I mean, everything in NWChem is parallel. And where there are codes where it's like, oh, well, we have a parallel version of this part of the code and that part of the code, but the rest is serial. So, and yet at this sort of critical juncture, it's sort of harder and harder to get sustained block funding for a project like NWChem. Apparently, we need to cure cancer because that seems to work for NAMD. So,
AIDS is better.
Cure AIDS. Okay. So this is an example of this capital P means private, okay? So that is the, when you have sort of the interface and the implementation. So there's interface headers and there's implementation headers, and these are all the different places that the private headers have been included in other parts of NWChem, thus guaranteeing that anything in these interfaces is baked in until someone unwinds this mess. And the real reason is because compilers apparently don't inline well enough, or Fortran semantics don't help, or whatever else. But don't do this. I mean, unless you're going for a Gordon Bell Prize, make a branch and say, this is my evil branch for this month that we will burn after this is over, and do it. Do all your awful hacks, and then undo it, because otherwise you end up sort of spaghettiizing your code for all time. So NWChem, I think, has been wildly successful. So I'm really criticizing only because if you don't criticize, you sort of can't learn anything. And NWChem is one of, I will say, 3 original gangsters of application co-design that I know about. Flash and NAMD would be the other 2. People really working together, math, computer science, domain people, in close collaboration for long periods of time, treating each other respectfully, and not just sort of saying, oh, you give me code, but actually trying to loop around on what are the right ideas. And interesting enough, they talk about hardware co-design. PNNL actually still does practice hardware-software co-design. They spec their machine to run NWChem, and then they optimize their machine for NWChem, and they loop around on that. So, if you run NWChem at PNNL, you will actually be running on a machine that is specifically procured to run NWChem very effectively. So that's good. It's bad news if you don't buy a machine like PNNL. Sometimes you find that you don't have enough memory per node or things like that, but that's a different issue. I don't know many codes that have ridden the wave of MPPs all the way from Intel Delta, which Paul knows a lot about the Delta, I believe. I don't know if anybody else in the room does. And then KSR is a platform you can read about it on Wikipedia, all the way to the modern Cray and Blue Gene series. So this is the same code, with constant evolution, of course, running across 2 decades of massively parallel platforms.
Robert Harrison was the equivalent of an early science project on the Delta.
Okay, yeah. So that's how that. So they were obviously and now early science on Blue Gene Q. So NWChem has been an early code on a lot of new machines. So and global arrays has been wildly successful. So it's relevant that many, I think last time I counted, 8 different quantum chemistry codes were using global arrays for parallelism. MPI is actually sort of the ugly duckling in quantum chemistry because people realized that what NWChem had come up with was a very, very good solution for that domain, and PNNL wisely made sure that GA and NWChem were separate enough that other code teams could go off and take GA and run with it. So this is something I think that, this is a good example of taking a layer cake and actually cutting it in half and giving it for 2 different kids' birthday parties or something like that. And NWChem, I think, is also successful because it was doing good methods, fast algorithms, and in parallel, they're all at the same time. It wasn't just old algorithms with parallel or new algorithms without parallel. I remember reading, there's a guy who's a very good computational chemist, did his habillation and tried to basically reproduce or do something similar to what NWChem had done, and he found basically he couldn't do it, and part of that had to do with the network hardware he was using. But NWChem was able to do good methods and do them very, very well in a lot of different directions, and that's something to aspire to. NWChem is incredibly productive for science, so regardless of how much Fortran-oriented teasing I do, the ultimate goal of computational science is science. If you're a software company, you should do software, but the real goal of scientific research labs is produce papers and knowledge, and NWChem is clearly wildly successful at that. Some of the things that NWChem should fix or has fixed: the development community is, I would say, not open. I mean, it's open in the sense that if you want to join it, you can knock on the door 3 times and you can get in at some point. But it's not, the repo is not public. You can download the latest release tarball, get the source, hack on that, and then merge upstream and things like that. I have write access on the repo, but I'm like one of 15 people that do. I would say that I would like this to change. There are reasons why people don't do it this way. There's reasons why NAMD isn't on GitHub. Some of it has to do with funding and the development practice and culture of code within communities, but if it was me, I would put the whole thing on GitHub. I won't tell you whether or not I've actually done that because the license allows me to, but it's not an official copy if it's there. I think NWChem, like many codes, suffers from sacred code disease. So the beauty of version control is that you can delete code and it doesn't disappear from the universe. And one of the things that frustrates me is the amount of dead code, some of which I've created, that's still in the repo. And I'm not even sure I should go in and clean up all my code because I never know when somebody's going to get mad and say, oh, but I was going to use your dead code. We should get rid of stuff, not just dead code, but just stuff that's not important. Unless it's really essential, why waste time trying to develop it? Why waste time maintaining it, dealing with compiler bugs related to it? Why maintain unit tests and run nightly unit tests on things that no one else cares about because those methods are antiquated? The broken abstractions have led to some spaghetti. It's crazy, but NWChem includes a copy of BLAS that it builds itself if you don't give it BLAS. And you can't even link that BLAS externally because they've overrode the error handler. Now, there's a good reason to override an error handler so that you get proper exception handling and some things like that. But it is frustrating that even though NWChem is a collection of 30 different libraries, linking any one of them against another quantum chemistry code is a mess. I've tried to do it. I've never succeeded in linking anything non-trivial because there's just too many spaghetti dependencies. And we should clean that up. But of course, there's no glory in it, so it's hard to do. I wanted to introduce OpenMP into NWChem years ago and was sort of told, well, we haven't made, they haven't decided what they're going to do yet. And they still haven't decided. So I just forked it and added a whole bunch of thread stuff anyways. We need to refactor for thread safety. This is the 21st century. We've had multi-core since I think 2001. You cannot live without threading and thread safety. The GA programming template is latency sensitive, so there's a blocking get, which is, from a performance standpoint, the worst form of one-sided, because you have to get data, it has to come all the way to you, and you're waiting for the data to arrive before you act. It's by far the easiest to use, and that's why it's there, but if you scale out the machine and you become latency sensitive, it becomes an issue. And there's a centralized load balancer that was never designed to scale to petascale, but because it worked well enough from 100-way parallelism, it's still being used. And this is the type of thing where it's sort of, you never really know, you have no idea how long your code will stick around. So if you have an idea that you know is sort of a Band-Aid or it's good enough for today, if you know that the wheels are going to fall off 5 or 10 years down the road, it would be good to document that and start thinking about the replacements. This is an incomplete list. Obviously, it's extremely self-centered because I know what I'm doing more than other people. NWChem is thankfully open source. The first 5 versions were not. That had something to do with their intended application goal of modeling nuclear waste and export control, but it was never, there's nothing in the code that was ever an issue, so it was just sort of inertia. But it's been open source. It's actually not copyleft. You can put it on Bitbucket if you want. It's perfectly legal, and you can redistribute it. Although chemists won't trust you if you do. There's a lot of performance tuning going on at Berkeley, Argonne, PNNL. I know that the Super SciDAC Institute is working on NWChem. Both my group and people at PNNL are working on load balancers based on work stealing and static partitioning to go beyond centralized schemes. PNNL has done a bunch of work with GPU offload for some of the compute-intensive kernels. We've been working on OpenMP and Intel Mike. And then there's lots of science work still happening. Now that we've sort of become feature complete, people are adding to NWChem really state-of-the-art science methods. People won't always like it when I say unhappy news, but without disruptive development, it's very challenging to think about NWChem at exascale. And you'll notice the explicit typo for a reason. Disruptive development is expensive. Just maintenance money does not get you 1,000-way increased parallelism from petascale to exascale. So we attempted to resolve that, and it was unsuccessful. So there's going to have to be something's got to give with respect to investing in the type of algorithmic advancements that are required to go the next 10 years of computing. So I'm going to talk about Madness a little bit. There's lots of info. Robert likes to joke about his terrible skills at naming software. Obviously, you can imagine when you Google this, you do not find the project homepage immediately. So I've shared it with you. I don't know if the 6 dashes are help with name resolution or not. If you do Robert Harrison Madness, I think you find a Stanford historian or psychologist who deals with psychological problems. So anyways, there's some issues there, but I think if you just go to Google Code and look for it or something like that. So Robert worked on NWChem for many, many years, and then he moved on to Madness. And many people falsely interpret Madness as, oh, this is just another quantum chemistry code from Robert Harrison. This is not at all the case. So Robert realized that there was a lot of opportunity in taking the ideas that were successful in NWChem and broadening applicability. So this is really designed to be a numerical framework. It's sort of like a PETSI, but I don't know that that's fair to either to say that. It's different, but it's designed to be useful for lots of different simulations. So there are currently major efforts to use it for chemistry, nuclear physics, atomic physics, material science. The climate and fusion stuff I'm less familiar with, but basically Madness can solve PDEs, and therefore you can solve lots of science. It's also sort of a parallel programming environment with really, really, I guess, crazy, hence the name, ideas. So you have a notion of a global namespace, things called futures, which are sort of, CS hardcore crazy business that don't really have a standard implementation, things like active messages. There's actually a lot in common with the ideas in Madness and with Charm++. It was certainly an inspiration when Robert was coming up with this. So this represents sort of the ideal of what Madness is trying to do and why it's a numerical thing and not a chemistry code. The goal is to write code like this, which I hope you can read. The slides are online if it's too fine. That's math, or something like math. And this is the graphic visualization of solving the Poisson equation. And that works. So this is Robert's demo, so I don't have the code for that. But you really can solve problems with that level of composition. There's, of course, a whole lot of magic that happens under the hood to make that possible. But the goal of Madness is to give the application programmer operators that allow them to compose the physical problem they have, rather than a whole bunch of highly domain-specific subroutines that act on arrays or something like that. The other thing that Madness does in the quantum chemistry domain and others is it actually solves the math problem differently. So the way we do traditional quantum chemistry, we tend to write things in the form of an eigenproblem and a differential equation. You can actually transform this to an integral equation and use Green's functions. And that I can't really go into any detail about that in the time that I have here, but it really fundamentally changes a lot of the properties of the implementation to just go with a completely new math. And you can achieve higher accuracy. You don't have the same numerical instabilities as you do in the differential form. You can put in your boundary conditions into the Green's function and just iterate on them, and they will be correct. And the integral form allows you to do things with low separation rank and decoupling, and exploit sort of the smooth properties of the Coulomb operator and, for fast algorithms and things like this. So the things that sort of learned from NWChem, Madness is actually a project with probably less than half of the people are domain scientists. There's sort of one domain scientist for every domain, maybe more, although in fact the nuclear physics work is done by a mathematician, George Fan, who's driving a lot of the math work and also working with the nuclear physics SIDAC project. So it's very, very heavy on CS and math people. Part of the reason you don't need 20 chemists to write the chemistry code in Madness is that it is easily composable, and it's actually a fairly, it's a few, I think it's maybe 2,000 lines of code now for the entire DFT module. It doesn't do everything NWChem's DFT code does, but it is blazingly fast for what it does. Robert is a big fan of asynchrony, so Madness, like NWChem, is really based on an asynchronous programming model with an implicit parallelism, meaning you don't think about, here I am, what's my process rank, and what do I do? You don't see the only place in NWChem you will see the rank is if you want to print from rank 0 just so that you don't print from everyone. Madness is similar. If you start up Madness, you type in it and you go off to the races, and you can say, if I'm rank 0, print. I mean, we could abstract that away if people don't want to see the rank 0 anywhere. And then it's essentially always on parallelism. There's no notion of, okay, now I'm going to go parallel. You write in Madness and you run it whatever parallelism you ask for at launch. Madness is sort of making smarter decisions in terms of design, uses MPI threads in C++, so you can do object orientation and generic programming the right way. MPI and pthreads are uber portable. There's the non-portable bits are really in the thread runtime. So it turns out things like spin locks are really, really sensitive to your CPU memory model, your bus, your operating system. You have to do very different things. Apparently, I haven't tested this myself, but they had to redo the spin lock implementation when they ran on the Amazon cloud, because the cloud has all this virtualization and it doesn't quack like a normal operating system with respect to busy polling on a memory location. So this is sort of, we're in the middle of transitioning to TBB, at least as the sort of default runtime, and keeping the other one only for fallback. And then we'll sort of punt the problem over to TBB, and then people like me will have to port TBB to BlueGeneQ, which we already did. But that sort of separation of concerns and we just say, well, if somebody wants to sell us a machine to run Madness, they have to help us with TBB. GPUs are sort of the one architectural portability target right now. There has been work, there's a paper on Madness on GPUs. I think the way most of us look at it is that's really NVIDIA's problem. You need fine-grained control of parallelism and low latency, a whole bunch of things that GPUs, throughput processors, don't let you do. So be it. As crazy, there's a bunch of people who look at the code and think it's insane, but we really do have coding standards. We use portable C++, C++03 right now. There's optional 11 stuff but there's always a way to work around it because we don't have that with some compilers. It adopted a lot of ideas from GA, from Silk, from Tron++, and from Chapel, but it doesn't use code from any of them. There are various reasons for that, but MPI and p-threads are everywhere, and so they're a good place to start. And it's currently portable from the cloud to your MacBook to BlueGeneQ and the Cray Cascade architecture. And yeah, it's successful in a lot of respects. So the architecture, here's another cake. You have your domain science sitting on top of a mathematical and numerical framework, sitting on top of a parallel runtime, which sits on top of some ugly guts that people like me look at. The nice thing about this separation is it really does allow efficient development. So I never look at this. This scares me a lot. I'm not good enough at math to look at multi-resolution analysis implementation. I spend most of my time writing C-style bare metal code inside of Madness for BlueGeneQ so that where thread time was efficient and correct. And then every once in a while, I look at my colleague's DFT code, which he writes up here, and basically, we don't have to look at each other's code. If I make the thread runtime better on BGQ, his code runs faster. End of story. Another one of our colleagues has spent time in this sort of dynamic load balancer and memory usage, and he doesn't have to look at the assembly bits that I've had to write, and he also doesn't have to look at the exchange correlation functional library interface that our other colleagues had to write. So it's a very good separation of concerns. Just a little, I don't have detailed performance. Mainly because I'll just say it's homework, download the code and build it and run it on BlueGeneQ and see what it does. This is a good example, I think, of a good decision to delay concerns. Madness didn't have parallel linear algebra. Even though there's some serious linear algebra in the initialization, they just called LatePack, because LatePack is everywhere, and ScalaPack has this built-in distribution that you have to deal with. It sort of forces you into their worldview of distributed data structures. Why bother doing that if you know that that's not right? So just use LatePack, and it turns out that wasn't really a problem until we came to BGQ, because the single node or single thread performance of BGQ is less, and we have greater concurrency. So when we started to run some beefy problems on BlueGene, we started to see, we spend 1 hour in LatePack on one node to initialize our initial guess, and then we go off to the races, and the rest of the simulation takes 10 minutes. So at that point, we said, okay, we care about this. And so we looked at Eigen, which Eigen is not distributed, but it's C++, and we were mad at Fortran, so LatePack had some thread safety issues we were afraid of. So Eigen doesn't help the performance, but it helps the I hate Fortran disease. And then we went with something called Elemental, which I talked about, I think, last week. And what do you know? You go from 700 seconds in the eigenvalue problem to 1.5 seconds, and you stop caring, and life is beautiful. Once we compiled Eigen, it was easy. XLC and templates are not our friends. I believe we just looked up whatever you guys did at KAUST. We have a tech report where we show in both cases, it's like 5 lines of code. You just basically cast a matrix, you initialize it, you call the methods, and you're done. Yeah, the other thing in terms of performance, you'll say, well, how does Madness calculation of 213 waters on 256 nodes compare to NWChem? I really can't tell you, because NWChem solves things in a localized Gaussian basis set. Madness solves things in a pseudospectral, multi-resolution adaptive basis set that has systematic convergence to some full numerical limit. NWChem's convergence is not systematic. It may get unstable as you go down to basically, if you're in a local basis set, your sort of immediate convergence is very fast, and then you sort of get to an over-complete basis that's not helping you and just leads to instabilities, whereas Madness it's a telescope, wavelet-like telescoping series that allows you to converge a lot faster or a lot more smoothly. So these are sort of near converged numerical calculations. I can't compare them to plane waves or something. So some things I think Madness can teach people. I'm sure this will make some of the Python fan people in the audience happy. I didn't mention it before, but there was a complete version of Madness written in Python, not oriented at massive parallelism, but back before they knew what the answers were in terms of their abstraction model, their parallelism, what sort of concurrent interfaces, concurrent objects do they want. Before they really understood all the math, they were developing in Python because Python allows you to do things fast and be nimble. And so they had a full version of Python. And then once they sort of realized what the right ideas were for their mathematics and their formulation of the problem, then they switched over and started the C++ version. Outsource portability to standards rather than trying to become a standard yourself. And I think that this is probably the most essential thing. Madness did not attempt to be a better NWChem. NWChem is a very good Gaussian orbital-based quantum chemistry code, and it has some plane wave features. There's no reason to just take the same algorithm off the shelf and do a better implementation of it if there's a better algorithm out there. So the better algorithm in this case is the integral equation formulation of quantum mechanics that allows you to get a whole bunch of different properties, and nobody had really implemented that in a general way before. And so it's an opportunity to do something new from an algorithmic sense, a method sense, and do a new parallel way. So you get something new in multiple axes, and it's interesting. Like with the LAPAC thing, don't solve a problem prematurely. The Newtonian premature optimization is the root of all evil if it interferes with agility. So if they tried to bake in a parallel eigensolver 5 years ago, it would have been Scalapack, because elemental didn't exist 5 years ago. And if they'd baked in Scalapack, they would have been stuck with block cyclic till the end of time, like some codes that use Scalapack. Whereas by waiting until we come along and we get elemental, it turns out we were able to integrate elemental in a completely non-disruptive way, and it took about a month. Madness has an open development model. I mean, you can't, of course, write to it immediately, but you can do an anonymous checkout and send patches to the list. It's GPL, which I personally hate, but it's better than not being open source. It's on Google Code. It's like the Dos Equis meme of we don't always write code, but when we do, we only do it on trunk or something like that. I don't know what a release would look like in Madness. We just have a trunk and we use it. And if we break the trunk, we fix it very quickly because that is what we use. I think something in terms of culture that people talked about earlier, the authority in the Madness project is very much proportional to the lines of code one writes. The two people who write an enormous amount of code are Robert Harrison, who's the PI, who obviously has authority, but not because he's old and funds the project. He has authority because he's written like 200,000 lines of code in the last 2 years. The other person who has a great deal of authority on the other end of the spectrum is a graduate student from Virginia Tech who is a supremely talented programmer. And when he says, hey, guess what? I'm factorizing the runtime this way. You guys have to change. People listen because he writes enough code. People are going to listen to him. So we have a completely meritocratic authority model, which is good. I have authority only on the things that I've written code on, which is perfectly appropriate. We have, annual developer workshops. We have workshops often enough, and then whenever we get together, we do pair programming and hackathon stuff. NWChem has tests of features, but not of sort of individual units of code. Most people would agree now, in hindsight, that that's not ideal. Madness has a whole bunch of unit tests. I don't know if it's Jenkins or one of the equivalents to Jenkins, but somebody's working on a sort of an automation build bot to do all sorts of regression testing for us, because that's really the pro way to do it. And then we try to adopt the best practices from commercial things. We use Google Test, we use Google Perf tools. We do a lot of integrate, like Google Static Analyzer, LLVM Static Analyzer. We were going to try to use Intel Thread Checker, but we had problems with the compiler. Anyways, we try to adopt sort of the absolute best practices for people who are, all of our bugs that are hard to debug have to do with threading and race conditions, because those are just hard. And so we try to use the tests that people use, or the tools that people use who do that kind of stuff for a living. And once again, I think I ran out of time, so you can look at the slides. I think it's pretty self-explanatory. I will skip to the end and thank my... Oh, I have another half an hour? No, you don't want to, anyway. So I will cover one part of this because I think this is important. So MPI+X is very much the future. The part I want to cover last last time on fork join, I think is self-explanatory from the slides. It's in the first slide deck that's online. But I think this is something I've discovered lately. It surprised me, and I wrote an IEEE TCSC blog post about it if you want the full version. I guess it's linked there. Okay. You know, MPI+X is, it's easy for one person to decide, right? So you're going to do MPI plus OpenMP. But somebody else might do MPI plus pthreads, and somebody else might do MPI plus TBB. And when you start composing those things together, you may occasionally run into issues. And so that's what I'm going to try and describe a little bit of. And this comes up for us. It's actually immediately came to my attention because of Madness. So Madness uses MPI with either direct use of pthreads or TBB using pthreads. Elemental, when we started using Elemental uses OpenMP directly and uses OpenMP in BLAS. Elemental also has its own library that it is interfacing with called MR-cubed, which does a tridiagonal solve in the eigensolver, which we were using. And MR-cubed uses pthreads. So right there you have pthreads, OpenMP implicit, OpenMP explicit, and now up in Madness we have pthreads explicit or pthreads implicit. So we've got a whole lot of different, we got 5 different places where we can initiate a thread creation. And that's totally cool if your OS lets you create, 16,384 threads before it grinds to a halt, like I think my Mac did earlier today. BlueGeneQ doesn't like this, and actually no supercomputer will behave well if you oversubscribe them. I know you could technically do it on Cray Linux, but if you try to touch the network from an oversubscribed thread, I don't know exactly how that works. You have to sort of do funny things, I think, to get the state to work. Here, and this is also a problem even if you use OpenMP, so only OpenMP. So the Livermore guys I was talking to a couple weeks ago were saying that if they're on a Cray machine and they use an OpenMP library built with the Intel OpenMP compiler, and then they use one built with the GCC OpenMP, and then they use one with the Pascal or the PGI, then they get 3 different OpenMP runtimes all firing at the same time. And for performance, for latency-sensitive purposes, they tend to busy pull. So bad things happen. Furthermore, to add to this, some of these threads might actually make MPI calls. So I guess you guys have been beaten to death with the right way to do MPI. I hope you've absorbed all 757 pages of the MPI-3 standard by now. But you're not supposed to make multiple calls to MPI or calls from multiple threads into MPI unless you use MPI thread multiple. Although you may discover that MPI thread multiple has high overhead or isn't supported by default in any number of situations. So what does this mean? Let's go back to Madness and Elemental. So the way Madness solved this, because Madness had to deal with the OpenMPI and Cray, both of which have problematic support for MPI thread multiple, at least historically, Madness had its own mutex. It has its own MPI mutex. Madness was doing MPI calls and mutexing itself, playing by the rules, and then Elemental came along and made MPI calls, and the machine room caught on fire because we violated the MPI standard. So then what do? So the problem is that the Madness mutex is not part of, it's not something that you can link into Elemental. We use it, or you could use it, but then now Elemental would be dependent on Madness, or we'd go into if-def hell. And then vice versa. So Elemental has its own ability to mutex around MPI, and Madness doesn't know about that. So now we've got 2 different independent ways of satisfying the MPI standard with threads serialized, and it's just totally broken. So the only sane way to work around this is to use MPI thread multiple. So this is the reason I bring this up, is because someday you guys might be in a computational science team talking to someone from a vendor or an MPI implementer group, and they might ask you about how you want to use MPI. And even if your application scientists will tell you they don't need MPI thread multiple. They'll say, oh, I use fork join or whatever, I don't actually need this. Well, if you ever want to have composable software, you might actually need this, because you'll end up having 2 completely well-designed MPI+X libraries using MPI thread serialize that will now be completely broken when attempting to coexist in the same universe. And so if you're a library developer and you are using MPI+X, you need to think very carefully about how you'll interface into applications that do the same thing. How do you as a library expose or abstract away whatever you want to do, how do you play nice with applications and other libraries? So the good news is on Blue Gene Cube we have excellent support for MPI thread multiple, and therefore as a Blue Gene Cube fanboy I can say neener, neener, neener to everyone else. But as a Madness developer or as an elemental person, that's obviously not satisfactory. So I'm not giving you an answer. I'm just I'm hopefully telling you something that maybe you don't know about and maybe you'll run into. So when you think about MPI+X, it's really MPI+X plus Y plus Z, or even with 3 different vendors, MPI plus X GNU plus X Intel plus X PGI can lead to problems. So you have to think very carefully when you go down the road to MPI+X and how you interoperate with different things. There's also really, really fun stuff, and by fun I mean absolutely terrible, when you start trying to interface with PCI devices and things like that from pthreads. You can read the CUDA thing about what happens when you pin CUDA devices to pthreads and try and switch them around. At one point I looked at it and it scared me, and I haven't really gone back to it. So there's a lot of fun stuff like that. So I think I probably summarized the whole blog post, but you can always read it if you care. The other solution, of course, which my MPI colleagues would say is perfectly cool, is use MPI+X where X equals MPI. There is, in fact, actually a supercomputing paper called MPI plus MPI, advocating that being a great programming model. And it turns out there are a whole bunch of reasons why that's actually not a bad idea. And some of the features in MPI 3 allow you to do things that solve some of the problems that people try to solve with threads. You can now solve them just with MPI. But then, of course, you need to have if-def MPI 3, as we talked about last week. So now I really am done. I have to thank a lot of my colleagues and mentors, particularly Robert for giving me a lot of the ideas for this talk, and then a bunch of my colleagues who've worked on Elemental and Madness and MPI and NWChem, and I have to acknowledge I'm supported by obviously Argonne, DOE, and NSF. So thank you.